examples using partial fraction decomposition. These will all be fairly simple examples in that they're only going to have linear factors, and none of those factors will be repeated. Also, all of the expressions that we're looking at are going to be proper rational expressions, meaning that the degree in the numerator is lower than the degree in the denominator. So let's start with this example. So my first step in partial fraction decomposition is to propose that I can decompose this. So I have two linear factors in my denominator here. So what I actually want to do is I want to get one fraction with each of those as its denominator. And I want to find an A and a B that'll make that happen. So now that I've proposed this, I don't want to work with fractions anymore. And if I multiply by this denominator to each piece, so if I take the denominator and multiply here, the denominator will cancel with what I'm multiplying by. I'll just be left with 2x plus 1. If I multiply here, then the x plus 1 that I'm multiplying by will cancel with this x plus 1. So what's left over is a times x plus 2. Then finally, with this piece, when I multiply times x plus 1 times x plus 2, the x plus 2's will cancel. I'll be just left with b times x plus 1. Now I want to strategically choose specific x's to make my life easier when I'm trying to find a and b. So if I want this term to be 0, I can make this 0 by letting x equal -2. That'll make this whole term disappear. I can do the same thing over here by letting x equal -1. Then this term will disappear. So let's try each of those, see what happens. So I get 2 times -2 plus 1 from the left side. Then we chose x equals -2 to make this factor 0, so we're taking a times 0, this term is going to disappear. Here I have b times -2 plus 1, so -1. So here I get -4 plus 1, that's going to be -3, that's equal to -b. Well, that implies that positive b is equal to positive 3. So there we go. We know one of our unknowns. Now all we need to find is a. But we chose this value specifically to make this term disappear, so let's actually use it. We have 2 times -1 plus 1 from my left side. This term will disappear because we chose -1 to make this term specifically 0. So I have a times -1 plus 2, or 1. So 2 times -1 will give me -2, plus 1, I get -1, and that's just equal to 1 times a, or a. So I have both of my unknowns, so I can write this as a partial fraction decomposition now. I can write -1 over x plus 1 plus 3 over x plus 2. I've decomposed this fraction. Let's look at the second one now. This one doesn't look like, at least not immediately, we can use partial fraction decomposition. I don't see separate factors in the bottom. But if we look more closely at this, this is actually a quadratic that we can factor. We want to think of two numbers that multiply to be 3 and add to be 4. Well, that should be x plus 3 and x plus 1. Now this looks like something we can use partial fraction decomposition with. I'm going to propose that I can write it as a over x plus 3 plus b over x plus 1. So I'll multiply these three pieces, I don't need to worry about this because these two are the exact same thing, by the denominator here. So I end up with 1, because the denominator will cancel with what I'm multiplying by. Then my x plus 3's will cancel, so I'm left with a times x plus 1. And then this last piece, the x plus 1's will cancel, I'll be left with an x plus 3 times b. So now I need to think about what values of x I want to use. Well, to make this 0, I need x equals -1. That'll make this term disappear. If I use x equals -3, this term is going to disappear. So if we go through with this, our left side is always 1, and we chose -1 so that -1 plus 1 is 0. This term is going to disappear. So I have b times -1 plus 3, or positive 2. So 1 is equal to 2b. If I divide by 2, b is equal to 1/2. Now, let's go through with x equals -3. The left side is still 1, and we chose -3 to make this term 0. So this term is going to disappear. So I have a times -3 plus 1, or -2. So a, when I divide by -2, will be equal to -1/2. b is equal to positive 1/2. So I can rewrite this as -1/2 over x plus 3 plus positive 1/2 over x plus 1. And there is our partial fraction decomposition. Let's look at this third example. This one is written nicely for us again. We have two linear factors. So I propose that I can write this as a over 2x plus 4 plus b over x plus 5. So let's get a polynomial to work with. So I need to multiply by this denominator to each piece. So I multiply this whole fraction by this. So I 2x minus 4 times x plus 5 times the fraction. This will cancel with what I multiply by. I'm just left with a 7 on the left side. Now I take this first piece, the 2x plus, this should be a minus 4, excuse me. The 2x minus 4 will cancel with the 2x minus 4. I'm just left with an a times x plus 5. And then with the second piece, the x plus 5's will cancel. I'm left with a b times 2x minus 4. So now we need to choose our x's. So if I choose x equals -5, that'll make this 0. So I'll have one term that disappears. Now this one's a little bit trickier. I need to think a little bit more. What will make 2x minus 4 equal to 0? Well, if we can't think of that off the top of our head, we can always just solve this equation. Or we can think that 2 times 2 is 4. So if I put in a positive 2 there, it will give me a 0 for this term. Okay, so let's start with x equals -5. The 7 isn't going to change, that just stays. Then we specifically chose the -5 so that -5 plus 5 is 0. This term disappears. So we have b times 2 times -5 minus 4. So 2 times -5 is -10, minus 4 is -14 times b. If I divide by -14 on both sides, I get that b is equal to -1/2 when I simplify that. When x is 2, 7 stays the same again. Then this term becomes a times 2 plus 5, which is 7. And then this term becomes b times 2 times 2 minus 4. Well, that's 0. That's why we chose x equals 2. So this term just disappears. This one, if we divide by 7 on both sides, we see that a is just equal to 1. So to write our partial fraction decomposition here, we get 1 over 2x minus 4 plus negative 1/2 times over x plus 5. There we go. So that this is equal to that once we find a and b. So hopefully we're feeling fairly comfortable with using 2 factors. Let's try one now with 3. This would be number 4. So we have x, we want it to be over x plus 1 times x plus 2 times x plus 3. And we want to decompose this. We have 3 linear factors in the denominator now. So we're going to decompose it into 3 separate pieces. We'll have a over x plus 1 plus b over x plus 2 plus, give ourselves more space, c over x plus 3. That's my proposal. This is what I want to find my a, b, and c for. So let's find the polynomial again. I don't want to deal with these fractions, so I multiply by this denominator here, 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 and here. So when I multiply this fraction by x plus 1 times x plus 2 times x plus 3, it's going to cancel with the denominator. All that I have left is just an x. This first fraction, the x plus 1's will cancel, but I'm left with the other 2 pieces. So I have a times x plus 2 times x plus 3. Here, the x plus 2's will cancel, so I have a plus b times x plus 1 times x plus 3. Those are my leftover pieces. And last but not least, here, the x plus 3's will cancel, so I'll have c, and then my other 2 pieces left over. Now this polynomial is longer and more complicated than the other ones, but we're going to do the same thing. We need to choose 3 values of x now to make sure that we can find our a, b, and c. So if we want x plus 2 to be 0, we're going to have to choose x equals negative 2. That will make this term disappear, and also this term disappear. So we'll be able to solve for b. Now, if I let this term be 0, I'm going to have x equals negative 3. That'll make this piece all 0, and it'll also make this piece 0. We'll be able to solve for c. So in order to solve for a, I need this piece to also be 0, so both of these will be 0. So I need x equals negative 1. So let's actually go and solve for a, b, and c now. So if x is negative 2, my left side is negative 2. We chose negative 2 to make this cancel, so this term is 0. This term will not be 0. I have b times negative 2 plus 1 is negative 1, times negative 2 plus 3 is positive 1. And then this term will also be 0 because this piece is 0. So what I end up with is negative 2 equals negative b. That implies b is equal to positive 2. So now we have one less unknown. Now what about if x is equal to negative 3? Well, my left side will just be x equals negative 3. And then this piece will be 0. Negative 3 plus 3, 0. So that term will disappear. This piece will also be 0, so this term disappears. So we're just left with our c term. So we have c times negative 3 plus 1, which is negative 2, times negative 3 plus 2, which is negative 1. So what we end up with is negative 3 equals, this will become positive 2 times c. We can divide by 2, we get c equals negative 3 halves. So now all we need to know is a. this should give us a, right? So our left side is going to be -1, because it's just x. And we have a times -1 plus 2, which should be +1. And then -1 plus 3, which will be +2. This term will be 0 because this will be 0. This term will be 0 because this is 0. So this is all we have left. So we have -1 equals 2a. So if we divide by 2 on both sides, we'll get a equals -1/2. So let's write our decomposition now. So we have -1/2 over x plus 1 plus 2 over x plus 2 plus -3/2 over x plus 3. So we followed the same steps, nothing really changed, it just was a little bit longer. Okay, let's look at another example where we have 3 pieces. So let's take x squared over x minus 1 times x squared plus 5x plus 4. Now here's another one where it doesn't immediately look like we can use partial fraction decomposition. But this can be factored, right? I have x minus 1. And if I look at this, I need 2 numbers that multiply to 4 and add to 5. Well, that should be x plus 4 and x plus 1 for factors. So now we have the exact same situation we did over there. 3 linear factors. So I want to propose that I can write this as a over the first one plus b over the second one plus c over the third one. Then I can multiply through by this denominator all the way across. So this term, when I multiply, will cancel with the denominator. I'll just be left with an x squared. This piece, the x minus 1, will cancel. I'll just be left with a and the second 2 terms. So x plus 4, x plus 1. Here, I'll be left with a b times x minus 1 times x plus 1, because this term will cancel, the middle one. And then c times x minus 1 times x plus 4. So I have another long polynomial. Let's find our 3 values of x now. So if I want this piece to be 0, I need x equals -4. That'll also make this term 0 because I have it here. So that'll leave me with my b term. If I make this piece 0, I need a -1 for my x. That'll make these 2 terms 0, I'll be left with c. If I make this 0, I need x equals +1, and that'll make these 2 terms 0, so I'll be left with my a. So this should do it. So, for x equals -4, my left side is going to be -4 squared, or 16. This piece of this term will be 0, so this term disappears. This term is also going to disappear, because this will be 0. So what I have in the middle is b times -4 minus 4, which is -5, and then -4 plus 1, which is -3. So I get 16 equals 15b. I can divide by 15 on both sides. b is equal to 16 over 15. 1 unknown down, 2 more to go. Let's see what happens when I take x equals -1. Well, -1 squared is +1. This term will disappear because this will be 0 if x is -1. This term will also disappear because this will be 0. So I'm left with c times -1 minus 1, which is -2, and -1 plus 4, which is +3. So I get 1 equals -6c, or when I divide by -6 on both sides, c is equal to -1/6. So there are 2 of my unknowns. This should give me the third. So 1 squared is also 1. And then I have a times 1 plus 4, which is 5, times 1 plus 1, which is 2. But then this term is going to be 0, this term is going to be 0. So this is all we have. So we get 1 equals 10a. So a is equal to 1 over 10. So let's go back up here and put these in. So we have 1 over 10 over x minus 1 plus 16 over 15 over x plus 4 plus negative 1/6 over x plus 1. So I just put those in for a, b, and c. If you had written your factors in a different order, you may have different values for a, b, and c. As long as they line up with the same factor and you got the same values here, then it's fine. It doesn't matter what order they're in as far as these can be shuffled around. Okay, one more example. We want 5x squared minus 8x plus 2 over x cubed minus x. Again, we want to decompose this. So at first glance, this is a similar example where we don't see how this can be decomposed. We also don't factor cubics very much. But this one actually isn't difficult. Because notice what each of these terms has in common. They share an x in common, right? So if I pull an x out of both, then x times x squared would give me that x cubed, and then x times minus 1 would give me that minus x. So now I've factored into a linear factor and a quadratic factor that happens to be the difference of two squares. So that's easy to factor. We have x times x plus 1 times x minus 1 as our denominator. Now we have three linear factors. We can think of just an x as a factor as x minus 0. So let's propose a decomposition. So I propose that we can take a over x plus b over x plus 1 plus c over x minus 1. So starting here, let's multiply all the pieces by x times x plus 1 times x minus 1. Here that'll cancel because the denominator is that. So we get 5x squared minus 8x plus 2. Here the x and the x will cancel, so we're left with a times x plus 1 times x minus 1. Here the b and the x, or the x plus 1 and the x plus 1 will cancel, so we're left with b times x minus 1. And then our last term, we're left with c times x plus 1, because the x minus 1's canceled. So let's choose our values of x. Again, we need 3. In order to make this piece 0, we need an x equals negative 1. That will make this term 0 and this term 0. So we'll be able to solve for b. In order to make this term 0, we need an x equals positive 1. That'll make this 0 and this 0, so we'll be able to solve for c. And then last but not least, we need x equals 0. That'll make this term and this term 0. We'll be able to solve for a. So let's take x equals negative 1. 5 times negative 1 squared will be 5. Minus 8 times negative 1 will be plus 8 plus 2. This term will be 0 and this term will be 0. So we're left with b times negative 1 times negative 1 minus 1, so negative 2. So 5 plus 8 plus 2 will give me 15. And then this will be b times positive 2. So b, when I divide by 2 on both sides, will be 15 halves. So there's our first piece. If x is equal to positive 1, 5 times 1 squared is 5, minus 8 times 1 plus 2. This term will be 0 because this right here will be 0. This will also be 0, so this is 0. So we're left with c times 1 plus 1. So 5 minus 8 is negative 3 plus 2 is negative 1 is equal to 2c. I can divide by 2 on both sides. I get c is equal to negative 1/2. Last but not least, when x is equal to 0, 5x squared is 0 because 0 squared is 0. Minus 8 times 0 is 0. So the left side is just 2. Then this piece will be 0. This piece will be 0. I have a times 0 plus 1 times 0 minus 1. So I get 2 equals negative a, or a equals negative 2. So there are all three pieces. So if we rewrite this, we get negative 2 over x plus 15 halves over x plus 1 plus negative 1/2 over x minus 1.